Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 10, Lesson 5 on vertical stretching and compressing of functions. Now so far all we've done are horizontal and vertical shifting of functions, which left the actual shape of the function exactly the same. All right, but now what we're going to start to do is we're going to start to change the shape of the function by vertically stretching the function out or by compressing it in towards the x-axis. So let's jump right into it and see how that's done. All right, now so far we have now built new functions from existing ones by vertically and horizontally shifting the functions, as I just mentioned. Doing this did not change the shape of the function, just where it was located. Now we will change its shape by stretching or compressing it in the vertical direction. So let's get into it and start in exercise number 1. The function f of x is a vertical shift of the function y equals x squared. Write the formula for f of x below. All right, so now you're supposed to be able to look at this function after the work that we did with stretching and, vertical shifting and horizontal shifting, but this is just a vertical shift. And you're supposed to be able to build the formula of this function based on the fact that you know that it's a shift of that function. So go ahead and see if you can write down the formula for f of x. All right, well, we should know that this function has a turning point at 0, 0. This one has a turning point at 0, -4. So clearly f of x is just y equals x squared shifted down 4 units, right? Maybe I'll write that down real quick just so we have it on our paper. F of x is y equals x squared shifted down 4 units, so f of x is equal to x squared minus 4, right? That's got to be that formula. Now, of course, you could always take your graphing calculator out, put this formula in, and verify that you do get that graph, but the important thing is to be able to say, oh, okay, I know that's y equals x squared, I've just moved it down 4 units, so it's got to be y equals x squared minus 4. Now let's take a look at a brand new type of function in letter B. If g of x equals 2 times f of x, write a formula for g of x below based on a. Well, again, never, ever, ever forget about the principle of substitution. If I'm saying g of x is 2 times f of x, and I'm saying f of x is equal to x squared minus 4, then I can easily now say that g of x is equal to 2, and let's get good use of parentheses in here, 2 times x squared minus 4. That's it. Now, we can make this formula, I guess, look a little bit nicer, by distributing the 2 through the parentheses, in which case g of x is 2x squared minus 8. All right. And you should probably get in the habit of doing that, although, to be honest, if they said give a formula for g of x and you stopped right here, I would give you full credit because that is a legitimate formula for g of x based on f of x. All right, let's take a look at letter C. Produce a table of values for g of x and plot it on the same grid. All right, well, we've done this many times. Let's exit out of here. Let's grab our graphing calculator. I'm going to put in my original function just so that we have them both there. So I'm going to say f of x is x squared minus 4, just to make sure I have it. Now remember our second function, which I can't call g of x on here, but I'm going to say is 2x squared minus 8. There we go. Now, we will get our table of values in just a moment, but this is kind of cool looking, right? We can already see that we've got a different shape on this parabola than the original one. It's not simply a vertical or a horizontal shift. We've definitely done something a little bit different here. But let's now get our table of values. As always, to do that, we go into our menu, choice 7, split screen table. All right, our first one is f1 of x. I need f2 of x. Love the fact that it always has to ask me that. I need to now produce a table of values, so I'm going to just kind of go up here a little bit until I get to, well, I'm never going to get 24 in there, but I can get that one in there. So now I need to just copy down, -3, 10, -2, 0, -1, 6, etc. That means, of course, as always, I'm going to have to go to the smaller version of my calculator so that I can go to this full screen version over here. So here we go, hopefully, handheld only. always in front. View full screen, and let's get ourselves a table of values. All right, we're going to start it right here. And maybe give myself some more room. X and y. When x was -3, y was 10. When x is -2, y is 0. When x is -1, y is -6. When x is 0, y is -8. When x is 1, I need to go down here. When x is 1, y is -6. When x is 2, y is 0. And when x is 3, y is 10. We see that beautiful symmetry that always is occurring when we've got a parabola, but we're not going to worry about that too much now. Now that we've got our table of values, we can graph. -3, 10 is up here. -2, 0 is right there. -1, -6 right there. 0, -8. Whoops, that was 0, -9. Let's see if I can count. 0, -8, 1, -6, 2, 0, and 3, 10. That was actually pretty good. All right, and there's our g of x. Right? It's kind of cool, right? And what's really awesome about this is that literally, if you look at every one of the points on g of x, right, the y-coordinate is simply twice the y-coordinate on f of x. For example, at x equals -3, the original y-coordinate was 5, the new y-coordinate is 10. At x equals, let's say, -1, the original y-coordinate was -3, now it's -6. Maybe the one that's most obvious is the turning point, right? Its y-coordinate was at -4, now the new y-coordinate is at -8. And that makes sense, literally. G of x is just twice f of x, so every output is simply twice the original output. Let's see what happens when we multiply by a number that's less than 1. Let's take a look at h of x. Or sorry, letter D. Letter D, if h of x equals 1/2 times f of x, write a formula for h of x based on a. All right, well, why don't you go ahead and try to do that, and then we'll go over it. All right, well, let's do it. Right, h of x equals 1/2 f of x, so h of x is 1/2 times x squared minus 4. Remember, that's all f of x is. F of x is just x squared minus 4. Again, that is a nice way to write it, but I'm going to actually myself distribute that multiplication by 1/2. Of course, if I do 1/2 times x squared, I get that. But 1/2 times 4, of course, is 2. So this is the formula I'm going to have for h of x, 1/2 x squared minus 2. And just like before, we want to produce a table of values for h of x, graph it on the grid, etc. Pause the video, and why don't you go ahead and do that for yourself. All right, let's do it. So exit out of here. All right, bring open my calculator again. This time what I'm going to do is I'm going to, I'll just double click on this, go down. Oh, no, I don't want all that way. Here we go. So I'm going to use 0.5 for 1/2 just because it's going to make my life a little bit easier. So 0.5 x squared minus 2, right? That was our answer for that one. Again, right away, it's a little bit hard to see because of all this sort of mess on here. Let me move f of x2 out of there. The black graph here now is my h of x. Not very easy to see that. Let's go over to our table. And let's go down and grab F3. All right, there we go. Now we've got some like messy values here. All right, and I don't need to write down all the messy values. I really don't. But I'll start here, you know, with -4, 6, and then I'll probably put in -2, 0, etc. All right, but I've got my table of values again for F3, which is the same as h of x. Again, pardon me for having to go to the small screen. It's just what I gotta do in order to keep the two on the same screen. Let me move this up a bit and move this over a bit. So we will start with an x and y, and I'm gonna start with an x value of -4 and a y value of 6. an x value of -2, a y value of 0. You can, of course, put the more messy ones in. There's nothing wrong with that, but I think I can get a pretty good sense for what's going on with all of this. 0, -2, 2, 0, and 4, 6. That should be good enough to get myself a decent graph. Now I'll just put this away, go back up, let's plot them. Whoops. Oh, I'm not gonna be able to keep this on the screen. We'll give it our best shot. Here we go. -4, 6 right here. -2, 0 right here. 0, -2 here. 2, 0. And 4, 6. And this now becomes our h of x. Okay, there they are. And again, what's really cool is that you can literally look at all of the y values here, and they are simply 1/2 the value of the y values on our original function, not on our second one, but on our original one. And that makes sense again, because all I'm doing is taking this formula, which gives me the y values on our original function, and multiplying it by 1/2, right? Or dividing by 2, however you want to think about it. Now, let's take a look. We've kind of got our graph here. It's a little bit easier to see now. The black is the original one. That's our f of x. This one down here is our g of x, and our red one is our h of x, okay? Letter F. How is the graph of each function changed when the transformation y equals k times f of x was performed? All right, well, I've kind of basically already gone over this, but, right, when k was equal to 2, right, then what happened was f of x was stretched vertically and got more narrow. Right? So literally, it's like I took that graph in black and I just went like this, like that. And it kind of makes sense because, again, every single one of those y values was multiplied by 2. On the other hand, when k was equal to 1/2, f of x was what we call compressed. And got wider, right? And again, that's where we've got this black graph and we went like this, right? Every single y value got sliced in half. And again, the effect of it in this red graph is it almost looks like the parabola got wider because, well, it did, right? But the most important thing to understand is that every single y value on that red graph is 1/2 the size of the y values on the original graph. Now, this is kind of important, the final piece, letter G. Were there any points that did not change their location? Which points and why? This is kind of cool. There's some points that when we did these vertical stretches and compressions didn't change where they were located at all, and they never will under a vertical stretch or compression. Pause the video now and think about which points they were. It should be, I think, pretty obvious on the graphs, but you never know. Take a moment to think about this. Well, it's simple. It's where the graphs intersect, right? And that's here and here, right? The zeros. The zeros didn't change. Now, why is that? And why will it always be the case that when you vertically stretch or compress, then the locations where the function crosses the x-axis won't go anywhere? They're what are called invariant. Very fancy word you don't need to know. Invariant, okay? Now, why do the zeros don't change? Well, keep in mind, right, when we have something like k times f of x, right, at the zeros, f of x is equal to 0. And when you multiply 0 by k, it is still 0. Right? The idea here is that, forget about vertical stretching and compressing. We're basically taking all the outputs and we're multiplying them by a number, right? If that number is larger than 1, well, then it stretches the thing. If it's between 0 and 1, it compresses it, and we'll talk about all that in a moment. On the other hand, if the output is equal to 0, it doesn't matter what you multiply it by, it's still going to be 0. So the zeros of a function never ever change under a vertical compression or stretch, okay? They certainly do when you vertically shift a function, but they don't when you simply multiply it by something. All right, let's summarize, right? When a function is multiplied by a positive constant, we'll see in the next lesson what happens when we multiply it by a negative constant, but when we multiply it by a positive constant, then its outputs, or y values, are all multiplied by that constant, and either get farther away from the x-axis, that's the stretch, or they get closer to the x-axis, that's the compression, right? Now, it's real simple, vertical stretching and compressing. The transformation y equals k times f of x will stretch the y values by what we call a scaling factor. That should sound familiar from dilations in 8th grade, but will stretch by a scaling factor when k is greater than 1, okay? So if we multiply anything by a number greater than 1, it's going to get larger and it's going to stretch it away from the x-axis. On the other hand, k times f of x will compress the y values by a scaling factor of k when k is between 0 and 1. Now, I'd love to be able to just say when k is less than 1, but that would include negative values, and there's a whole different ballgame involved when you multiply by negative values. And this, by the way, should look a little bit familiar also to what we talked about with exponential functions, right? Exponential functions grow if their bases are greater than 1, and they decay if their bases are between 0 and 1. And again, it basically gets down to the fact that if you multiply by a number larger than 1, the result gets larger, and if you multiply by a number between 0 and 1, the result gets smaller. Same idea here. So let's get into some examples of vertical stretching and compressing. Exercise number 2. The function f of x is shown below. It's known as a sawtooth function. By the way, there are many sawtooth functions. This is just one of them, but what a great name for a function. Another function g of x is defined by the formula g of x equals 4 times f of x. Great. All right, letter A. What is the range of the function f of x? All right, don't worry about g of x. What is the range of the function f of x? Why don't you go ahead and answer that question now? Well, remember, range is the y values, right? These are the y values. The range are the y values. So I look at my sawtooth function. I see that the lowest y value that I ever hit is down here at -2. The highest y values I hit are up here at +2. So the range is simply, I'm going to do this in interval notation, -2 to +2. That's it. That's my range. All right. Now, letter B, right? Using the definition of g of x above, determine the value of g of 0. All right, this should be pretty easy. Pause the video now and forget about vertical stretches or compressions or anything. Use this particular formula for g of x to figure out the value of g of 0. Pause the video now and go ahead. All right, well, I'm just going to do function notation on this formula, right? G of 0 is 4 times f of 0. Now, what is f of 0? Well, f of 0, I come over to the graph of f of x. I see that f of 0 is equal to 2, right? The output when the input is equal to 0. So g of 0 has got to be 8, right? Now, of course, what that immediately tells me, even though the problem doesn't ask, is that the point 0, 8 must lie on the graph of g, right? And that's kind of cool. It tells me that this point, right, underneath this transformation is going to all of a sudden go all the way up here, right? That y value of 2 all of a sudden is going to be multiplied by 4 and become a y value of 8. So easy. Let's take a look at letter C. Show where each of the turning points of f of x will get mapped when transformed into the graph of g of x. All right, so we've only actually got 3 turning points and we already know where this one goes, okay? But we know that what's going on here is that every y value is going to get multiplied by 4. So this point here, which is at -5, -2, will end up going to -5, -8, right? I am simply going to be multiplying its y value by 4. I'm not multiplying the x value by 4. Nothing's happening to the x here at all. And likewise, this point, which is also at 5, this one's at 5, -2, will then get mapped to 5, -8. The other turning point we already sort of did, but let's do it again anyway. 0, 2 will end up getting mapped to 0, 8. Okay? So now, right, in letter D, it says, using C, draw a graph of g of x. Well, okay, great. So I know this point ends up going up here. I know this point ends up going down here. I know this point ends up going down here. Now, you know, I might want to include 2 more, which are the endpoints. Now, those aren't technically turning points, although they would be if we continued the graph out here, right? Those would end up being turning points. And again, it's easy. I can go to this point. I can say its y value is currently 2. Then I multiply everything by 4, and it also goes up to 8. And the same thing is true over here. So I now can connect these like this, like that. Again, really should be doing it with a straight edge. But not necessarily the greatest. There it is. These things should be straight lines. Let me actually label this g of x. All right, awesome. Now, letter E. How many solutions are there to f of x equals g of x? Now notice, in letter E, they're not asking me for what are the solutions to f of x equals g of x. They just want to know how many there are. Pause the video now and see if you can answer this question. Well, again, remember, anytime you're solving this equation based on a graph, right, it's all about intersection points. It's all about intersection points. That almost looks like the word intersection, maybe not quite, but I tried my best. 1, 2, 3, 4. 4 of them. And if you notice, of course, where are those 4 intersection points? They're at the zeros, because the zeros don't change under a vertical stretch. All right, let's keep going. Now, we can use important features, especially things like a function's maximum or minimum value, to help us understand how a function has been vertically stretched or compressed. So let's take a look at exercise 3 to see if we can see how that works. The quadratic function f of x equals 9 minus x squared is shown on the grid below, along with g of x equals k times f of x for some unknown value of k. Letter A asks us to state the maximum value for each of these functions. All right, this is easy enough. Now keep in mind, when I ask a question like what is the maximum value of a function, I'm always referring to the y value. I'm never referring to the x value unless I literally say what's the maximum x value. But when I say what is the maximum value for each function, I'm asking for the largest y value. So pause the video now and tell me what f max is and what g max is. Take a moment. All right, well, the largest value for f occurs up here at its turning point, and that's equal to 9. All right, the largest value for g of x occurs right here, and that's y equals 3. By the way, even if I didn't know that this was a vertical stretch or compression, I could tell it was because, again, take a look at those zeros. See how the two functions intersect at their zeros? Anytime those zeros are fixed, I should at least suspect that I have a vertical stretch or compression. Now let's take a look at letter B. Based on the fact that g max equals k times f max, what is the value of k? Be careful here. Pause the video now and see if you can figure out the value of k. boy, it would be tempting to think that k is equal to 3, wouldn't it? You know, you look at this 3, you look at that 9, and you think, oh, that one is 3 times as much as that one. Except we're looking for it the other way around, right? G is equal to k times f, so literally 3 is equal to k times 9. That means 3 is equal to 9k. I can divide both sides by 9. K is equal to 3/9, which is equal to 1/3, right? And that makes sense because I've compressed this function, right? All the y values on the red graph have come closer to the x-axis than the y values on the blue graph, on the graph of f of x. Now let's take a look at letter C. Write a formula for g of x and verify by graphing both f of x and g of x on your calculator for the same window. All right, so see if you can produce a formula for g of x, given that you know, right, g of x equals k times f of x, and you know f of x is 9 minus x squared. Pause the video now and go ahead and see if you can write a formula for g of x. All right, let's do it. So, g of x equals k times f of x, right? G of x equals 1/3 times 9 minus x squared. Again, that's a lovely formula for g of x, but I'm going to distribute it through that multiplying factor. 1/3 times 9 is 3, and 1/3 times x squared is 1/3 times x squared. So there's my formula for g of x. G of x is 3 minus 1/3 times x squared. Let's graph them both. All right, let's try to graph them both. Let's bring out our graphing calculator. Here we go. I'm going to do a brand new doc just to make it easy. Add a calculator. No, that's not what I wanted. I wanted a graph. Here we go. That'll do. Good enough. So I'm going to put in my original one, which was 9 minus x squared. All right, we'll get it in the proper window in a moment. Now let's put in our next one. And I want 3 minus, I'll even use the fraction bar. 3 minus 1/3 times x squared. Okay, and maybe that's probably good enough, but maybe I'll adjust the window real quick just so that we can make sure that we see it look exactly like it did before. Window settings, those are good. -10 and 10. Okay, let's take a look. I'm gonna do handheld only, full screen, and let's move it up and let's compare. Even the colors match. How great is that, right? Again, a little bit hard to see. Let me actually go here and there. That's a nice comparison. Okay, and it really, really hammers home, right, the fact that we got our k right? If we thought our k was 3, we would have gotten a completely wrong answer, right? But given that we've got that k correct, we've distributed it correctly, everything, we've got the right graph. All right, let's wrap this thing up. Vertical stretching and compressing. It's so simple, right? It's actually very simple or similar to vertical shifting, right? When we vertically shifted, we added or subtracted a number from every single y value. Vertical stretching and compressing, we're going to take every y value and we're going to multiply them by a number. If the number is greater than 1, right, then what's going to happen is that the graph is going to get stretched away from the x-axis. Every y value will get, or every point will get farther from the x-axis by that factor of k. On the other hand, if k is between 0 and 1, 1/2, 1/3, 1/4, 1/10, whatever, right, then all the y values will get multiplied by that fraction, right, and they will all get closer to the x-axis because their distance is getting smaller. Okay, so it's actually pretty easy, and it's pretty neat because we can change the shape now of our graph rather than just moving it around on the coordinate grid. All right, we're going to see this more in the next lesson when we start to introduce what happens when k can also be negative. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking, and keep solving problems.